Okay, we're going to talk about section 3.1. It's on optimal values, the week of October the 26th, 2020. Obviously, you can read that from the screen, so I'm not going to bore you with all the other details. Okay, I'm adjusting the camera a little bit just because I can. All right, I went ahead and worked the warm-up with you. Basically, the best way to do the warm-up is to graph it. Actually, I'm going to show you some new things that will help you do a little bit better. But I went ahead and worked with you to save some time. Here we go. X equals 2/3 is the maximum for this particular equation. For the next one, y equals x to the third. There is no max and no min. You can check those by graphing it on your graphing calculator. And then this one, you can check and you will see that there is only one maximum, but there are two minimums. So you can check those on your own. Okay. Now, 3.1. Let's look at the following. Much of calculus is devoted to determining the behavior of a function of a given interval, or on a given interval, excuse me. We seek to know if the function has a maximum or a minimum value. We want to know when the graph is increasing or decreasing as well. This chapter gives us the tools necessary to find those answers to those questions, as well as real-world applications of these problems. Basically, you're going to be using your derivatives that you learned in chapter 2, and you're going to be applying them to what they really do. Now, you know that the derivative measures the instantaneous rate of change, such as the instantaneous rate of change of a constant is 0, as we have talked about in class. All right. Okay. Now, some things you need to know. The definition of the extrema. Let f be defined on the interval I containing c. F of c is called the minimum of, or f, sorry, I was losing my place, of f on I. When f of c is less than, it should say f of x for all of x in the given interval. Now, f of c is the maximum of f on I when f of c is greater than or equal to f of x for all of I on the interval. Now, the minimum maximum of a function on an open interval are the extreme values, aka the extrema. So when I say extrema, I'm talking about the extreme values, or in other words, stating the maximum or minimum of the given function on that interval. The max min of a function on an interval are also called the absolute maximum and minimum. Sometimes referred to as the global max or the global min on the interval. All right. Now, I want you to look at some stuff here. I apologize, PowerPoint's not always working with me, as you can see. Okay, now, you're going to see the same functions on different intervals. Okay, now, some of the graphs may or may not have a maximum or minimum on the given interval. Now, let's look at y. Okay, now notice that f is continuous on the interval -1 to 2, which is closed on both ways. Notice it has a maximum and it has a minimum. On the other hand, if you look at the next one, we have our function is continuous, but it's open on both ends. It's open from -1 to +2. You can see that right there. See, it does have a minimum right there because it's continuous there, but as you can see, it has no maximum because that's an open dot. Therefore, that function on that interval does not have a maximum, but as you can see here, it does have a minimum. On the other hand, g here, this function is not continuous. Even though the interval is closed, it's not continuous. There's an open dot right there, so therefore, there is no minimum, but there is a maximum. So the basic gist is, if f is continuous on the closed interval, then f has both a minimum and a maximum. So make a note of that. As long as the function is continuous on a closed interval, then it's going to have both a minimum and a maximum on that given interval. All right. All right. Now, relative extrema and critical numbers. In the figure, the graph has both relative maximum and a relative minimum, as you can see. They're right here. This is a relative maximum, and it's our relative minimum. The graph, the relative maximums are the tops of the hills, and the relative minimums are at the bottoms of the valleys, as you can see. So we got the hill here, and we got the valley there. For a smooth rounded graph, a maximum occurs when the tangent line is high or low. For sharp and peak graphs, the maximum occurs when the function is not differentiable. So that's the other part of it. For sharp peak graphs, occurs when the function is not differentiable. All right, now make a note here. Each derivative of the relative maximum from the previous example was either 0 or it does not exist. So now, one thing I do want you to note is this, and this is very important. The x values at these special points where the derivative is either 0 or it does not exist are called the critical numbers. And that's what we're going to talk about throughout the rest of this particular topic right here. All right, now, if there is an open interval containing C on which f of C is a maximum, it is what's called the relative maximum. If there's an open interval on which f of C is the minimum, it's called the relative minimum or relative min. So, all right. Now, here's a couple of examples right here. I'm just going to highlight them real quick. Sine of x. The critical number where the derivative of this is going to be 0 is at pi over 2, because if you derive sine of x, remember it's cosine of x, and cosine at pi over 2 is 0. Therefore, that is a relative, that's a critical number. Same thing right here, 3 pi over 2 is the other critical number. That's where, if you look at the rate of change, it's going up, it flattens, and then it goes down again. And then down here, it goes down, flattens, and goes back up again. So those are the critical numbers. Right here, at x equals 3 is a critical number for the following. If we were to derive this, it'd be the same thing. Now, with an absolute value, remember, the rate of change is negative, then the rate of change is positive. So therefore, it just has a relative minimum because it's going down, then it's going back up again. But right there is where the limits come together. That's an absolute value anyway. So, all right, but you get the idea of just how this works here. All right, now, each derivative of the relative extrema from this example was either 0 or it does not exist. And as you can tell there, well, you can see. So the x values of these special points are what's called the critical numbers. All right, now, the definition of a critical number is as follows. Let f be defined at C if f prime of C equals 0 or if it is not differentiable at C, then C is a critical number of f. So, you can see right here, these are two prime examples. F prime of C does not exist, so therefore C is a critical number. Same thing right here. F prime of 0, it's a horizontal tangent line, as you can see right there, so therefore C is a critical number. So if F has a relative min or a relative max at x equals C, then C is what's called a critical number of F. So remember, you're looking for two things. You're looking for where, when you derive it, f prime of x. When you derive it, at which values does f prime of x equal 0, or where does it not exist? That's what you're looking for. All right. Now, here are some guidelines, and I'll go over this, then I'll stop it. We'll do part 2, and then we'll do a couple of examples on part 2. All right, determine the extrema on a closed interval. Find the critical numbers. Evaluate f at each of the critical numbers. Evaluate f at each endpoint. That's the big thing, especially if it's on a closed interval. This is only on a closed interval. So evaluate at each endpoint. The least of these is the minimum, and the greatest is the maximum. So we'll do a couple of examples of those in part 2, but for right now, I'm going to pause this, and we'll continue with part 2.